I'll start with a disclaimer. So it's extremely easy to get really crappy performance out of an HPC system, and just to throw some numbers at you. So if you write bad MPI code, and this is from experience, you typically lose between 50 and 90% of your performance, easily. If you don't do node level parallelization, so you don't do any OpenMP or threading or something, you just use a single core, on a system like Myra or Titan, well, you lose another 94% of the performance because you just use 1/16 of the system. No vectorization, typically 75% gone. Bad memory access patterns, that brings you down, to 1% of the performance because you're constantly waiting on the main memory. And if you sum this all up, basically you get 785 gigaflops out of Myra. To put this in perspective, this is about what a modern GPU gives you, if you use it correctly. So that all being said, this is why you should care about application performance. Because if you don't care about this, you're right there extremely easily. Because, and I'm coming from a site where we have a whole bunch of users that pull some open source projects, do configure, make, install, and once they get, run some test input files, once they get correct results, they submit like 20,000 jobs of it. And never care about performance at all. So if you're aiming for a true high scale, and I mean you're here because you want to go work on those leadership systems, you're fighting for the CPU hours you get, you better make the best out of it. So this is why you should care about performance at all. Now the second disclaimer I'm bringing is performance tools won't automatically make your code run faster. If any performance tool claims this, it's a lie. They only tell you where to look, in good cases, or where you should put work in. In some cases, and this is not a disclaimer, like with Vampir, they are only able to show you things, and you have to interpret it yourself. So, nothing is for free in HPC. There is no free lunch in HPC. Anybody who claims otherwise is either a marketing guy or a liar. So, without further ado, what I'm going to talk about today is a little bit about the Vampir tool suite, what it does, what's the workflow behind it. So how does this work? How does this compare with a number of other performance tools that you've seen? I'm going to walk through the performance charts. So the mission behind Vampir is that we want to visualize. So the name of Vampir is actually an acronym. It says Visualization of MPI Resources. So there are two components. First, you have to collect data of some form. That's the so-called trace file that you've heard of before. And then you can visualize this. Visualizing trace files is a very powerful mechanism because so far there has been no other instrument that is as capable as the human eye in recognizing patterns and seeing things. So being capable of actually showing things enables someone who kind of knows what to look for. And now here comes the trick. I have to educate you what to look for. In actually finding performance bottlenecks and working through this. So the questions that you typically can answer with Vampir is, what happens with my application is a given process or thread. What is it doing at any point in time? What are communication patterns that I'm seeing? Are there any imbalances? The power of a trace file, and I'm kind of jumping ahead a little, is that a flat profile kind of summarizes everything. If you have like varying behavior, there are tricks to kind of track this as well. But in the end, if like your load imbalance kind of shifts around, and we've seen codes like this where like shifting window simulations, where you kind of, your simulation window kind of slides along and basically the processes that drop out in the end, you put them back in front. So then your load imbalances kind of, jump between processes because they're always like in the middle line of your simulation and in your overall simulation grid. So with this is extremely hard for flat profilers if your load imbalances flip around. So this is where traces are helpful. So kind of, sampling versus tracing, you've seen all this before, so, repetition. You do the audio now. So sampling basically means you interrupt your program at any arbitrary interval in time, and this doesn't have to be like a fixed interval. It typically is, but this can be any kind of interval you want. You take a sample and then you aggregate it immediately. Tracing means you modify the application so that it sends out events to a performance monitor that then records this and typically keeps a log file of this. Now, a little bit more performance analysis 101, because there are a whole bunch of terms that are used sometimes incorrectly. So this is how I'm going to use them. So there are data acquisition techniques when you do performance analysis. One of them is sampling. The other is event-based instrumentation. This is basically how you get data out of the application. The one is kind of push, the other one is pull. Then what you can do is you have to record this in some form. So you can summarize this right away, or you can log this. And no matter how you got the data samples, let's really call them like this, whether they are pushed or you pull them out of the application, you can either summarize immediately or log the sample or the event. And then if you present it, you can either do this with a profile or with a timeline. The only thing you cannot do is create out of a summary a timeline, because you've already dropped all this information. And then if you kind of look at the terms that are typically used, when you typically say profiling, you are kind of on the left side. So you immediately summarize and you create profiles out of it. This is kind of the flat profile approach. When you mean tracing, you typically mean you have an event log and you have timelines on top. The interesting part is how you actually acquired this data doesn't matter too much. So for example, SCORP, we've just developed a sampling interface as well, because all those upcoming C++ codes, they're just a hell to trace. All those small methods, they produce so many events that combining like sampling and event-driven instrumentation is a really nice approach to kind of keep the event rate at a manageable level and to keep the trace files below the 10 terabytes that we've already heard today. And the other way around, they are totally free to also create immediate profiles from events. Nothing prevents you from this. And this is actually interesting. While the colors kind of indicate how this was traditionally until a couple of years ago, in the past 2 or 3 years, things have changed that both sides have kind of embraced the other technique a little bit. Another thing that we've heard today is that the tracing is more complicated, produces more data, and I'm going to explain why that is. And I've used the cartoon that we did for supercomputing a couple of years ago to kind of explain why what our tool does. And I'm going to use an analogy. Who all had biology in school? Okay, who did microscopy there? Less people. So what you had to do to put a sample under a microscope, you had to prepare this, and you couldn't really look at a really large thing. So, for example, you want to study a fly. The profiling approach would be, take an easy tool of a magnifying glass, and then you see more. The normal way would be you look at it, so that's your the runtime has changed. That's weird, kind of the analogy in your computer program. And then you throw a profile at it, meaning I'm grabbing out a magnifying glass. I don't have to do anything to the probe itself, because it will use samples, and it will just, I can look closer at it. But since sampling rates are kind of limited, and so the level of detail I can get out of this is somehow limited by the tool itself. So then tracing, on the other hand, would be the microscope. Yes, it takes more time to prepare this, so there are steps you have to do to actually get the probe under the microscope first. So you have to do this instrumentation. This is the preparation of the probe. And yes, if you try to shove the whole fly under the microscope, this will be a whole bunch of data to look at, because you have to move it around, and so there will be a lot of images to actually look at. So you kind of have to decide first what you want to study explicitly on the fly by basically looking with a magnifying glass first. Oh, this seems to be an interesting part, then you dissect that part, and then you put this part under the microscope. Nobody prevents you from shoving the whole thing under the microscope, but there will be so much data that what you're actually interested in will or might be lost on you. Or the sysadmins will call you first that you've spoiled the file system. in the computer analogy terms. So what I'm going to show today is this combination of collecting traces with SCORP. That's the instrumentation tool that we use for Vampir, and then the visualization with Vampir. So what we're going to do is with Vampir, you have two methods of visualization. You have timeline charts that basically look like this. This is kind of what you've seen with Tau before, and thanks again for all the nice words about Vampir. So this is kind of, in the X direction you have time, and in the Y direction you have your processing streams, let's call it. Those can be processes, threads, GPU streams, anything you can record that's kind of a context, in a sense, in a computation context, can be such an event stream. And you can have summary charts that are, like your normal profiles that you can look at. So how does this whole workflow, give you the information that you can visualize something? Well, the easy part with SCORP is it also offers compiler wrappers. So you basically just put SCORP in front of your compiler calls in your makefiles, and then you should be good in 90% of the cases. In some cases, you have to hint a little bit more. For example, if you do MPI-CC and you're actually doing GPU computing underneath, so you need to link the CUDA libraries, then you have to add a -- CUDA. But this is basically rarely needed. There are sometimes, yes?
If you use CMake, this is not going to work. So any CMake project will break this.
And then there are ways to help there as well. So there is like this extra long documentation, which if it doesn't work without documentation, then it's not a good product. However, sometimes it's worthwhile to look at a man page. Actually, the -- help output also provides a lot of hints on which ways to try. And then what you would first do, and what also the default is when you use SCORP, it will run a profiling mode. So it has instrumented the application, meaning that at every function entry and exit, at every library that it understands, and this can be a whole bunch of them, I'm going to show them in just a minute, it will record as you're jumping in and getting out. And if there is additional information to be recorded, like MPI messages, CUDA mem copies, and so on, kernel invocations, it will also record those invocation parameters, how much data was pushed around from whom to whom, and so on. And then there's a SCORP score profiler that will generate you an appropriate filter on like the top 10 functions where you spent the most time in. And with this filter, this is basically, you've used your magnifying glass, you've identified the interesting spots kind of automatically. You can also do this manually if I don't want to study this one source code file, for example, or so on. So you can also add manual filters. And then you rerun with a tracing enabled using the filter that you just created. And by this, you kind of limit the scope of this very fine-grained analysis. Because tracing, are almost down at the processor clock level with a resolution you can achieve. So much more fine-grained than typical sampling frequencies. And then you load the trace file and you analyze it in Vampir. So what does the SCORP architecture look like? SCORP is actually a nice example of a working collaboration between multiple tool vendors. So there are a bunch of tool vendors, tool producers, or tools, Vampir, Scalaska, Tau, Periscope, that all had the issue that they wanted to do fun stuff in analyzing performance data. And the annoying thing that they had to do is they had to write tracing tools to actually acquire the data first. And at some point, the people said, we're all doing the same thing. Why don't we just come up with a common infrastructure so that we can do the stuff that we are interested in and spend less resources on the annoying stuff of actually acquiring the data first. So this is how SCORP came about. So it's a common measurement or performance gathering infrastructure for all those tools that can do profiling, profiles, and traces at the same time. And actually, it has just been extended so that it can do instrumentation and sampling underneath as well. So a very flexible tool. It can record anything, MPI, OpenMP, CUDA, OpenCL, not on the slide, but there's an OpenCL port as well. Compiler instrumentation, Tau PDT instrumentation, user instrumentation. So if you want to instrument, just want to look at a certain loop, for example, and track it, how it's iterating, you're free to do so. So anything that's out there. I've got OpenACC. We've also have a proof of concept for OpenACC, and we're working on a common tool interface with OpenACC that will then be supported there as well. So anything you're running on an HPC system can be recorded, and can be recorded by one tool simultaneously. So you don't have to throw multiple tools at the whole thing, which is kind of the disadvantage when you use hardware vendor tools. So the NVIDIA tools, for example, only can do NVIDIA GPUs. Some other tool might only be able to do MPI, and you kind of have to piece it together. Here you just run your application once, and you record everything that's going on. Also with the addition, if you can, it has POPI counters. There's like an additional flexible counter interface. Anything you can count, meaning you have a timestamp and a value, you can put it in there. So this way you also get, so we're also putting, for example, storage system counters inside. You know, how much I/O is going to disks at a current point in time during your application. So you can find, you can analyze the whole system stack in your HPC system and correlate it with what's going on in your application. Energy consumption. So we've also done demos with energy consumption, where you can see how much energy are actually various routines consuming. This is more like a scientific thing. There's no real good practical usage to it. But there are tons of things you can do. The great thing is SCORP is open source. So if you come up with something that you want to record, you just put it in, or you modify it, and you're good to go. SCORP is controlled through environment variables, so there are a whole bunch of things you can config at runtime. Basically, say I want the profile, I want to trace, how much memory am I going to use, where do you want to put the trace file, a filter file that you want to use, some PAPI metrics that you want to use, R usage metrics. And if you want the whole list of them, this is the command that you need to use to pull this. Now that you have the trace file, what do you do with it? Well, the one thing you can always do, there's like a profiling tool that will generate you a PDF file that you can hand off to your management and say, here, I've done all this analysis. Or you can interactively work with this, and this is kind of where the strength of Vampir comes in. You're walking through performance data, and you can look at any part of it. If it's small enough, and now here comes the limitation. For this interactivity, you need to be able to load the trace file into main memory. So look at the directory size of where the trace file is written. Take it about times 4. This is how much main memory you will need. If your laptop still has this, you can just open it there. If it's not, then I'll show you how to deal with that in a minute. So typically, you have like a small or medium-sized trace file that you've generated with SCORP, and you just start Vampir. If it's on your local machine, it has an icon. It pops up. And then you say open file, and you select the file, and we'll load it, and then you're all happy, and then you can start going. If your trace file gets a little larger, and it's not that hard to do this, then the interesting part you can do is that Vampir comes with a kind of analysis engine, and the analysis engine itself is just a parallel program. So the one that's running on my machine is just a multi-threaded version that will use all CPU cores that are available. And the same program is actually a hybrid program. So it does MPI plus OpenMP. And you can run the same program on your cluster. So the Blue Gene isn't really suited for it because it has so little memory per process. So that's why this recommended machine in Argonne is actually the the x86 visualization cluster. Since they have a common file system, you generate the trace file on Myra, and then you just run the Vampir server instance. So basically what you do, you have like a many-core program, and we've done proof of concepts on Jaguar and Titan that it actually scales to full system runs, provided that you do the filtering correctly. So if you don't, you'll get panicked phone calls from the sysadmins because you're filling up even the Lustre file system in Oak Ridge can be filled up easily when you turn on tracing and don't think about it. So you get a trace file that is then very large. Typically what also happens is you have like multiple files that you generate because we don't put everything in a single file. So there is some MPIO involved that aggregates some event streams into one file. And then you launch a Vampir server with a certain number of processing elements. And this only means how large you choose the number is how much memory you want. So you basically just calculate, okay, it's this large. So as an example for a Jaguar trace file where we generated 1.5 terabytes of trace data for a full system run, we used 20,000 cores to load it. And then your local GUI can connect to the Vampir server, where you basically just say, I don't want to open a local file, I want to open a remote file. You tell it where that is, so where the Vampir server is running. And then you, just like you saw with the DDT GUI that can basically hop onto a debugging instance that runs on an HPC system, the Vampir GUI also hops onto the Vampir server, tells the server what file to open, so the analysis engine then opens the file. And the only thing that gets transported across this wire is the display information, what the GUI is supposed to display. So all the data mining actually happens on the parallel machine, which has the benefit that even at 1.5 terabyte trace file, you can navigate interactively. And with navigating, I mean you get a response from the data mining within like 3 to 5 seconds. So very large trace files, you can still walk through them interactively. So I'm going to show Vampir now, and now I'm going to, show me hands. You want me to do this live on Vampir that I have on my laptop, or you want me to walk through slides that have some nice animations on them? Live. Hands up for live. Alrighty, so there we are. So now it's a ridiculously large font size that you wouldn't use on your laptop normally, but it's kind of for educational purposes in this case. So if you open up a trace file, in this case it's a 64 processor trace file parallel application. It ran on Eugene, that's a machine in Jülich. This is what it looks like when you open it up. You see a timeline right here, you see all the processes, you see an overall profile, and you see a context view down here, basically displaying all the information that it knows about the trace file. In Vampir, you can left-click on anything, and then in the context view, it will tell you what it is. So if I click on this up here, it will show me I'm in the display master timeline. I found a function of process 0. It's called function init and belongs to the group MPI. When it began, when it stopped, how long it took. I have a legend here what the colors mean. So in this case, green is application, red is MPI, orange is FD4, and probably you better know what FD4 is than I do. Some other part of the application, I guess. Up here, you have a thumbnail of the trace. And now let me show you having a trace file, meaning a full list of events is a cool thing compared to a flat profile. Because what I can do now, so this would be like a flat profile that I'm getting out of gprof or some other MPI-aware profiler. Because I have all the information, I can now click and hold and zoom into those 1.3 seconds of execution back here. And if you've noticed, this profile has just changed. I see up here in the thumbnail that I'm looking at this part of the trace file only. And so now I can basically generate profiles for any arbitrary interval in my program and dive into where things are actually happening. And I can zoom in pretty darn far. So if I'm going in here and here and here, I'm now looking at 0.1 seconds. So I'm looking at 2.4 milliseconds in this interval. we have traces where you're basically zooming down to nanoseconds, where you're seeing actually events happening on a couple of 10 nanoseconds intervals. So it's a very highly sophisticated event recording mechanism where you try to keep the perturbation at reasonable levels, but then again, this perturbation is only, or is directly proportional to the number of events that you're trying to push out. So if you're kind of, having this C++ code fully instrumented with tons of small methods, then yes, you'll easily see like 1,000% overhead if you do, because you've just shoved the fly under the microscope. And there's like tons of data coming out. The other thing you can do is you can right-click on anything in Vampir. And then you can basically change and work with displays. So one of the things, one of the annoying things you have right here happening is that, well, there are 64 processes down here, and I have to do this. Oh, it's not 60,000. It's 16,000. My apologies. So, well, a little bit more. Still opened locally here. So what I can do now, if I right-click this, I can say basically adjust the process bar height to fit the whole chart. So what I'm now looking at, I'm looking at 16,000 processes in one display. There's aliasing happening, but basically the aliasing algorithm is so smart to maintain the execution pattern for yourself. So it's doing statistics behind to keep the representatives that kind of maintain the overall overview, so that what you're looking here, basically the number of orange and red pixels resembles what you're seeing on the right in the profile. So that you could count now. But this is basically what's done to make this still a representative presentation of what's going on. If I'm zooming out now to all of this, I basically see the timeline of the overall program run. Interesting other displays I can add, or let me just walk through this a little bit more. The profile that I have up here, I can modify this to basically show a whole number of different metrics. So at the moment it's accumulated exclusive time. I can change this to a number of invocations. So what is called most often is typically a common question that you ask yourself. I can also say this average exclusive time. So how long are certain functions executed on average? I can select only certain processes. I don't want everybody, for example, or I want this as a pie chart and not the bar chart, for example. Or I can select that I don't want all functions, but I only want to look at MPI, so profile me only the MPI. Then I'll see that in this part of the application, the main time is spent in MPI init. Because it's not really long running, it's just 6 seconds. So that's not totally unexpected at 16,000 processes. So, or I'm looking at how much time am I actually spending in the generate me profile for over the user or over the applications group. So everything is an instrumented user application, for example. So a whole bunch of interesting things I can just do with a profile display. And the interesting part is, if I want to correlate things, I can easily say I want another one of these. So the pie chart up here just generates me another one. So I can now put things side by side, number of invocations, exclusive runtimes, and see how things correlate and find them. There are options down here. I can do this. Also show a total sum. I can group functions, so that I only see the 3 groups that are here, for example, so that I don't see individual functions, but actually, how does this distribute over the groups in the trace file? So a whole bunch of useful things. On the timeline side, there's the process timeline, which is basically a call stack of a single process. So once you've identified, that there's maybe one process that you're more interested in, then you can walk through its call stack and see, how it's calling functions, what's going on, how far it's going down. Another interesting thing, just for the fun of it, you can move things around and dock them wherever you want them to. So if I want the context display to be all over the bottom, I just move it all the way down here. So sometimes it's worthwhile to kind of play a little with this so that you have the information that you're looking for at the spot where you want it to be. So, just grab things and move it around. Let me fix this again, hopefully. Come on. Okay, so I'll put this over here. Other things you can do. One of the tools I find most useful with Vampir is the performance radar. Basically, what it allows you to do is to overlap performance counters, so anything that's countable, with a timeline. So it basically generates you a timeline of color-coded events. So you have a metric down here, for example, MPI latencies that is recorded. I can also say adjust the bar height to fit the whole chart. So I now see all the MPI latencies that are accumulated as a metric in the trace file as well. Some of the metrics Vampir can actually generate itself. So the metrics that are available you find here: message data rate, for example, message volume in transit, time spent in MPI wait. So I can see where in my program who is spending time in MPI wait. So I can zoom in here. If I want to basically have this more fine-grained, get rid of the blue, I can grab this down here at the triangle. But at this moment, you actually see right here, if you let me throw this out in the middle. So now I basically have the performance radar side by side, and you see actually you see the MPI parts up here, how they correlate with the metric down here. And now, wouldn't it be cool if you can actually put this all on top of one another? And the interesting part is you actually can. So let me show you what I believe is the coolest feature of Vampir. So I'm trying to get rid of this display. I can say the black lines are messages that are going on. So what you're seeing here, the black lines are messages. I can click on them. So it's a message, it's a point-to-point message, goes from which process to which process, how long it took, and what the size was, what the communicator was. So it records everything that is in the MPI send. So you can click on it. There are also statistical displays to walk through all this. So as I was saying, with the option, I can also say I want to include performance data, and then I can now up here I can say give me the time spent in MPI wait on top of this. Now I have color coded on top of this the MPI wait. So directly on top of my timeline, I can basically select the transparency right here. Do I want to see more of the underlying timeline, or do I want to see more of the overlaying metric? So here you basically see from yellow to red the overlaying metric, and I immediately see the correlation between this part right here in the MPI where I'm doing the MPI wait. So I can start correlating counters, and this counter could also be a floating point ops counter. So where are my floating point intensive operations? Where is this going on? Where are my cache misses happening? So anything you can count and record, you can include and directly correlate this data to what's going on when, and actually study things. So you can see everything. The interesting part is you being in front of this, kind of playing with having a certain level of expectation and knowing what to pull up. So MPI wait obviously is a bad thing. What you're basically seeing here is the topology of the system. Those bumps, how long it took for everybody to grab the results. So it's not too bad what you're seeing here. A couple of other interesting displays you can play with is the message summary, which basically allows you profiling over all messages that are included. And now a little word of warning, because the trace file format, so the only limit to what Vampir and Scorp can do is the trace file format. It has to be kind of agreed upon. And the format only knows of messages. So we are abusing messages for multiple things because like a CUDA mem copy is technically saying also like an MPI message. You're transferring data from one memory location to another. So the term message is kind of overloaded. If you have a GPU trace file that also contains MPI, your statistic will show you MPI and GPU messages at the same time. The great thing is that you can also filter things right here. You can basically say, I only want to see messages of a certain communicator, for example. Only show me profiles or only show messages of this size, and then if you deselect something, it will be removed from the timeline and from all profile displays. So you can actually dive through anything in your application and select and deselect anything that you're interested in or not interested in. So you can dive into really the parts that are interesting for you. So in this case, you can basically see a number of messages of what size. So the dominant message size in this application is 62K. And then the other message sizes, the larger messages, are less dominant. You can also say this, that the metric is not the, I'm interested in the message data rate. So how long did it take for messages of various sizes? What are the average message data rates that they achieved, for example? Yes?
In a message type, what about collectives?
Collectives are recorded, but they are you don't do the profiling over them. So you can actually see them, and there are some performance radar metrics you can generate for them that or that are included that will help you there. So for collectives, you're probably better off in looking at overlaying like runtimes, or you can or selecting various groups and showing them in the timeline. So a feature that I haven't shown, and there are like tons of features, so we could spend the whole evening on things you can show with Vampir, is that there are also filter functions right here. I can basically select on the main timeline to only highlight functions of various regular expressions in the end. So I can create a regular expression that says, only highlight me anything that's an MPI barrier, and then we'll basically show you in the trace file in the display anything that's an MPI barrier and gray out everything else. Yes.
Can you use more or less arbitrary arithmetic or logical operations to combine certain metrics? Like for instance, I want to see the flop rate only when
yes,
no communication on an adjacent rank.
Yes, you can. And this is, David had this wonderful slide. I didn't have the time to bring this up. One of the 5 coolest things I find about Vampir. So one of the thing overlaying this with a performance radar, with this transparency thing is definitely number 1. The second coolest thing in Vampir is you can customize metrics. So if you open a trace file, we try to generate some metrics that provide some meaning and that are very general, that you can use them in any trace file. You see them right here. Some are red because the necessary input is not there. So flops, because the trace doesn't contain any PAPI floating point counters, so it doesn't work. I/O bandwidth, so I/O was not recorded. So I/O functions were not traced. The interesting part is you can say add, and then up comes the custom metric creator, and now this is all drag and drop. You basically say I want to create a metric that is function is active, function count, some counter, message volume, whatever. I can add a metric, I can add an operation. I can, for example, say I want to do an add between this and that, and I just drag and drop things. I want to do logical operation is less than. So in case, your case, I only want to see this if it is greater than something. And then I built myself this. So as we started out with this, we thought about, doing something where you actually have to type this in, what you want to do. And then one of our students came up with this idea, why don't we just do it like this? This way is more intuitive. Everybody can play with this and connect inputs and outputs. Because before, people were discussing reverse Polish notation things, and I was like, this is not going to fly with users. How you want to do this? So So with this, you can create almost anything that you want as a counter. Whole bunch of useful things. The last thing I want to show you live in Vampir is, now I've undocked this and made this an own window. So kind of the same thing that you've seen with tau in 3D, we do in 2D, only with color coding. So, kind of take away the Z dimension and only imagine this with color coding. You see the number of messages exchanged between processes. You see mainly nearest neighbor communication here going on, and a couple messages going on in other directions. Things you can also say, the metric that you want is, for example, the maximum data message rate that you saw. And with this, it's sometimes very easy to find, hotspots or processes that are slower than others, where their maximum data rate that they achieve was much lower than anybody else. So in theory, you can also grab this. Now I can show you this. See, this is how this is supposed to work. So I can basically change the scale and, remove the ones that are higher than something, and, change, how this is all color-coded. To kind of dive into and find, outliers in this case. Let me show you something else. This was not work that I did. It was work that my student did. We've had wonderful discussions on making performance analysis easier and better, and guiding people to performance hotspots better. One of the things that we came up with is, we call it CASIDA, and this is an acronym I actually don't even know. It's basically a root cause analysis. It generates you a critical path over your whole application, no matter what the application is doing. So it doesn't care if you do MPI, OpenMP, pthreads, CUDA, OpenCL, whatever. We've written rules for all this, so that it will generate the critical path for you. And then it will, in this case, basically, this is the red overlay. So on which processes, or in this case, OpenMP threads on a Xeon Phi, are you spending? So who's on the critical path? And out of this, you can generate blame. So what are the functions that generate this? So who is responsible for, or who's a good optimization target? This is basically, kind of, you have the trace file, you run a tool on the trace file to kind of augment the trace file with additional information. So it's kind of an MPI program itself that reads in the trace file, does the critical path analysis, adds additional performance counters to the metrics. So it's kind of it's adding data to the trace file, and then you can open the new trace file in Vampir again, and then have wait time distributions and blame distributions. So penalty assigned on the wait state root causes. So this is kind of our poor man's approach at this as well. So in this case, if you see this, for example, we have like a GPU that's on the critical path because there's a CUDA context synchronized going on. So there's a host waiting for this. And the waiting, so the CPU is stalled. So in this case, it's aggregating blame right here. So you can overlay this, and because we can actually do this on a timeline, you can see where in your application is this happening. Is this like happening all the time? It's not like an overall statement going on. We have the overall statement on the right-hand side here because the profile is still there. The strength of Vampir is in the end that you can generate profiles for any arbitrary time intervals. Because of this zooming capability. If you want to only look at a certain phase in your program, well, you navigate right in, and then you profile just this phase of your application and look how this behaves, for example. So what Vampir and Vampir Server give you is this interactive trace and visualization and analysis that I've tried to demo right here live as well. I hope you found this almost as entertaining and sweating as I had up here. You have this zooming and browsing so that you can actually navigate through a whole bunch of things and do lots of things. The interesting part is that because of the decoupling of the analysis engine, that is a parallel program that's run on an HPC resource itself, you are even able to analyze large trace files. So you don't need to be afraid if your trace file has gotten a little out of hand. It might be just because it's all the data that you need and you want to work with this. There are ways to still to analyze this with reasonable performance. So we've demoed that we've dealt with 200,000 processes and very large trace files, and still be able to work with this. And it runs on the typical desktop operating system. We've done an Android port for supercomputing once, but it just isn't really tablet compatible because right-click on a tablet is just extremely difficult. SCORE-P is this common measurement infrastructure that tries to hide away as many of the complicated details as possible by providing kind of a standard workflow and lots of knobs to twist and turn as you're trying to distill the right piece of information out of your applications. So the expert mode that's included there allows you to record and do anything. And the interesting part, the trace file library, OTF2 library, allows you to actually manually modify trace files if you want to do own stuff to them. So if you want to do like this root cause analysis that started out as a project for us, this is basically using a trace file library and doing some rewriting of the trace files. So with this, there are like a whole bunch of people behind all this. And if you want to play with Vampir at Argonne, this is the website. Very well done compared to other customer sites. And it will also tell you how to get all this stuff, so how to get the software for your laptop and so on.
You mentioned OpenCL support. To what extent do you support OpenCL?
So so OpenCL is a little bit difficult because it doesn't have a standardized performance tool interface. So with CUDA we use CUPTI. That is the same interface that the NVIDIA tools also use themselves. For OpenCL we do library wrapping, so we kind of duplicate all the OpenCL calls and all of them. And so that way we, as you create contexts and so on the host, we record this and we can show this. As you transfer data, we record this as messages. So this is all visible. So this can all be recorded. This is basically what we did before CUPTI was around, also for CUDA. The good thing with OpenCL is that it's evolving so painfully slowly that you don't have to recreate those wrapper libraries every half year like you have to do with CUDA. So for CUDA, CUPTI is actually a blessing because it's kind of a standardized interface that is not changing at the same frequency as CUDA is, but almost. So it's only changing like with every second CUDA version.
Sorry if I missed that in your talk. Is the tool free?
Say again?
The tool free?
So SCORE-P is free, Vampir is not, and this is mainly political reasons. So Vampir is a product that we sell, but typically all the large DOE labs have a site license. So it's typically one of the software packages that is available on the large systems. And I believe the setup that you can get right here is with Argonne. If you have a project or you have an account on one of the machines, you can download a Vampir remote, we call it, which can only access a Vampir server. If you have an Argonne email address, then you can also get the Vampir standalone version that can do open local files and also connect to remote machines. So there are ways. So if you have an account in either like Lawrence Livermore, Argonne, or Oak Ridge, then you can basically grab it and use it and work with Vampir, so Vampir server on their resources.